Hello everyone, we are going to discuss the solutions of the exam taken on the 25th of May 2023 for the module Electrical Principles. We discussed this in the class, but this is just a quick review of the solution or marking a scheme. Question number 1, as usual, this is about converting from a scale of a unit to another scale. 400 kilovolt, how much volt? So we replace kilo with a number 1000 or 10 to the power 3. That's it. 350 microampere. 350 micro can be replaced by 10 to the power negative 6. And then here we are asked to make it like milliampere. We need to multiply this by the inverse of milli. Milli is 10 to the power negative 3, so you should multiply by 10 to the power 3. 5,500 nanofarad, how much farad? So, nano is 10 to the power negative 9. 5,500, you can either use the same value, the same, notation to representation, or you can write 5.5 times 10 to the power 3, because in this case 10 to the power 3 and 10 to the power negative 9 can be simplified to 10 to the power negative 6. D, 4.2 times 10 to the power 3 hertz, how much kilohertz? So obviously this 10 to the power 3 can be replaced by kilo, and that makes it kilohertz. 0.0005 microhenry. So micro is 10 to the power negative 6. This 0.0005, this too much decimal, can be written as 5 times 10 to the power negative 4. And then here we want to make it like picohenry. Pico is 10 to the power negative 12. We put the inverse of that one, which is 10 to the power 12. This is the inverse. Now you simplify, you see here you'd have 10 to the power 2, which is 100. 5 times 100 is 500 picohenry. Just remember, in the exam, it doesn't matter how you reach this final number. The full mark for each section, which is about 2 to 2.5 marks, are only given in case you get the right answer. So any algorithm, any procedure, any techniques you want to apply to get this final value here is not important, and you don't have to write it. While for other questions, starting from question number 2 onwards, you should explain the process or the way you got the final answer, and that has around 70% of the mark. The last section of this question says 630 micro-ohm, how much milli-ohm? So micro can be replaced by 10 to the power negative 6. Then we want to make milli, so we put the inverse of milli. You know, milli is 10 to the power negative 3, so we multiply this by the inverse of that one, which is 10 to the power 3. Question number 2 says there is a battery whose full capacity is 5 kilowatt hour or 5,000 watt hour. Currently only half of this battery, 50%, is full. It takes 30 minutes or half an hour to full this battery for storage. What's the power of this battery? Okay, power by definition equals energy divided by time or duration. The energy we need from now until we make this battery full is 50% of the full capacity, because now it is at the 50%, which is like half, and that is 2,500, because this is half of 5,000, no? So from 2,500 to 5,000, you need another 2,500 watt hour. So the energy you need is 2,500 watt hour, and the time in hours is 0.5. Be careful, even if in the question it is in minutes, you need to put it in hour here, because your energy here is in watt hour, not joule. So watt hour divided by hour is watt, 5,000 watt. Second section, B, The question is, what is the energy of this storage or battery in joule? So this section is independent from section A. Even if you can't answer section A, you're confused with this kind of calculations, at least you can do section B. So you know what is the full capacity of the battery, 5,000, but that is in watt hour. If you replace hour with seconds, which means you multiply this by 3,600 seconds, you get 18 million joule or 18 megajoule, which is the full energy or capacity of this storage in joule. Again, section C is an independent section from those two sections. It's about calculating the resistance of a material or conductor. Resistivity is given, the length is given, and the cross-sectional area is given. In this question, cross-sectional area is given. Sometimes diameter, radius is given, so you should calculate this cross-sectional area first. You should be careful for the unit of measurements. For length, 200 meter was given. In case that is kilometer, you need to convert to meter. The cross-sectional area is usually given in millimeter square. 10 millimeter square is what we got in this question. You need to convert it to meter square. That means you need to multiply this by 10 to power negative 6. You know, each milli equals 10 to power negative 3. But millimeter square is like 10 to power negative 3 square. 10 to power negative 3 square. So that is 10 to power negative 6. Yeah. Question number 3 is a usual question about calculating the equivalent resistance of a given circuit. The given circuit is this blue one. This is a combination of parallel and series resistances. Maybe in the first look, you can only identify some parallel resistors, but step by step, when you reduce the network, you can also identify some series connected resistors. I start from the right side of this circuit. These 2 and 3, they are series, so you can add them and replace by 5 ohm resistance. Then that 5 ohm resistor and this 5 ohm resistor are parallel. I just draw them here with green. So 5, 5, they are parallel. They are also equal. You can replace them by a single resistor with half of resistance, like 2.5 ohm. If they are not equal, you know how to calculate the parallel equivalent resistor. That is the multiplication of the two resistances divided by the sum. So 5 times 5 divided by 5 plus 5. In this case, as they are equal, that would be half of one of them, 2.5. Okay, so everything you see on this right hand side is reduced to a 2.5 ohm resistor. Then here there are 3 parallel resistors. One way to find the equivalent resistor here is to use that general formulation for parallel resistors, which says the inverse of the equivalent resistor equals sum of the inverse of all resistors. But I want to go through another way. I want to select a pair of resistors from these 3 or more parallel resistors. Then I will replace that pair of resistors with a single resistor, and then choose another one which is parallel to this equivalent one, and go like this step by step. So here I can take these two, 2020, and see what is the equivalent resistor here if I go to replace these two with a single resistor. So 2020, one way is you multiply them and divide by the sum. The other way is you say as they are equal, the equivalent one is half of one of them. So 20 divided by 2 is 10. So these two can be replaced by a single resistor with 10 ohm resistance. The new resistor, 10 ohm resistor, is now parallel to this 10 ohm resistor. Again, 2 parallel resistors with equal resistances. So the equivalent one is half of one of them. 10 divided by 2 is 5. So everything you see here, all these 3 resistors are now reduced to a single 5 ohm resistor. So I can redraw this circuit like this. This part is 5 ohm, this part is 2.5, and I had this 2.5 here. I see 3 resistors connected in series, so the total one equals sum of them 10 ohm. In this section A, another question was, what is the total current in this circuit? So total current is the voltage or total voltage, 100 volts, divided by the total resistor, which is 10 ohm. So 100 divided by 10 is 10 amp. In section B, the question is, what if the voltage is 60 volts? What is the total current and what is the voltage drop in resistor 5, this one? So before calculating the voltage drop of this resistor, I need to know the current here. And before identifying the current here, I need to know what is the total current in this circuit. So total current here is again total voltage divided by the total resistance. Total resistance is what you got in section A, while total voltage is this new voltage, 60 volt. Be careful, it's different from 100 volt, which was in section A. So 60 divided by 10, 6 amp. This is the total current injected by this battery, which flowed through this resistor and through proportionally through all of these resistors, and finally it is the same original value, 6 amp, and it reached this node. Now I want to know what is the current flowing through this branch. Okay, now if you look at these two branches, I mean this one and the other one, the right hand side one, you see the two branches have equal resistances, because this one is 5 ohm and this one is 3 plus 2, which is again 5. Look at here, 5, 5. So you have 6 amp which reached this node, and then it is divided into two parts for two branches with equal resistances. If resistances are equal, that total current is divided equally. So 3 amps goes here, and 3 amps goes there. If the resistances are different, like 5, and then on this part you had, I don't know, 8, then you should use current divider rule. But here we are lucky, we don't need current divider rule. Okay, so current flowing through this 5 ohm resistor is 3 amp. So you need to multiply this 3 amp by the same resistance, this 5 ohm, and you get voltage. This is called voltage drop at resistor 5, or R equals 5. Question number 4 is usually about AC circuits. And the AC circuits, the first part is we want you to calculate reactances. Sometimes only inductive reactance, sometimes inductive and capacitive reactances. In this case, we have both of them. Inductive reactance equals 2 pi FL. F here is 50 Hz. Be careful, sometimes it's 60, sometimes it's 50, not always it's 50. L is inductance. Inductance, if you check the question text, that is 200 millihenry. So I multiply 200 by 10 to the power negative 3, because that is millihenry. Okay, you work out this and you get 62.83 ohm. For XC, which is capacitive reactance, be careful, you need to make the inverse of 2 pi FC. 1 over 2 pi FC, not 2 pi FC. That is a common mistake I see. Okay, 1 over 2 pi FC, so that is 1 divided by 2 pi F 50 Hertz, and then C, or capacitance, is the one given in the question. That was 80 microfarad. If I'm not wrong, 80 microfarad, so that is 80 times 10 to the power negative 6, which is a replacement for micro. So you can calculate this using your calculator, simply multiply them and then make the inverse, and you get 39.78 ohm. Section B is usually about the impedance. The total impedance here equals square root R square plus X square. But X is a general term to define the total reactance of the circuit. Here the total reactance is the difference between the two reactances XL and XC. It doesn't matter if you deduct XC from XL or XL from XC. But it's very important that first you make the difference, then you make the square, not the square of each one. Okay, so we use this formulation, and the rest is just replacing the parameters with the numbers. 35 ohm for the resistor was given in the question, and XL, XC are what you got in section A. Section C, current. What is the total current in this circuit? I equals V divided by Z. So V is 120 volt, and Z is what you got in section B, 41.9. And then the question in the end is about what is the angle between current and voltage. That angle is actually the angle between R and Z. And to obtain it, you can use this formula. Or if you remember the impedance triangle, you may use sine or cosine as well. But this is commonly used, tangent inverse x over r. V equals tangent inverse x over r. X is again the difference between XL and XC. And you can work out this one. You just need to use an advanced engineering calculator to find out what is the phi if its tangent equals 0.66. I didn't do this in the class. That's for you, you can obtain it. But then you need to draw the phasor diagram. Always you can start with this voltage vector, a horizontal arrow like this, maybe from left to right if you like. Then for the current, it's important to look at the XL and XC. If XL is greater than XC, which is the most common thing you see in building services, if you look at a system, an overall system, XL normally is greater than XC. We say that is lagging. Lagging, you see, current lags the voltage. Voltage is ahead if you consider counterclockwise direction as the opposite direction of the phasors. So this system is lagging. The other way is when XC is greater than XL and you say that the system is leading, then you draw current on this direction to this direction. Question number 5 is about transformers. Here the ratio of transformer is given, primary voltage is given, and the secondary voltage is the question. So we know N1 over N2 equals V1 over V2. 1 over 5 equals 410, which is the given primary voltage, and then V2. So this is, you see, this is a step-up transformer. It increases the level of voltage 5 times. So if you give, or if you feed 410 volt to this transformer, in the output you get 2050 volt. Section B is about secondary and primary currents. The load power is given, and you know here usually we say load is actually on the secondary side. And V2 or voltage of the secondary side or load is also given. The ratio of transformer is given. This is a step down transformer like those used in building services. And then question is, what is I2, I1? I know this ratio also for current. You see this one, N1 over N2 equals I2 over I1. But if I use this one in the beginning here, although I have N1 over N2, which is 10 to 1, but I don't have I2 and I don't have I1. So this doesn't work for me in the beginning. But the good news is, in the secondary side, I have both P2 and V2. So based on power definition, which says P2 equals V2 I2 or P equals VI, you can find I. And this is I of the secondary. Now you can use this principle of operation of transformer. Now you got N1, you got N2, you got I2, and easily you can obtain I1. And section C of this question is saying, what if power of the load is 2.5 megawatt? Okay, again, you use the definition of power here, and you use this new power to obtain current. Be careful with the unit of measurements and the scales. If they say megawatt, you need to put 10 to the power 6. If they say kilovolt, kilo, 10 to the power 3. Be very careful with these units of measurements. Question number 6 is a system in which they say load is dissipating maximum power, and they say that power is 50 watt. The resistance of the load is also given. The first question says, what is the current flowing through this load? Okay, I have this definition for power, which is actually a derivation of the main formulation of power, P equals VI. And if you replace V by R times I, you can get this one. Or you can memorize this one, P equals RI squared. So I equals root square P over R. Both of them are known. P is known, which is 50, and R is also given, 10 ohm. So the current is 2.23 amp. Section B is with the original assumption saying power dissipation in the load is maximum. Find the internal resistance of the battery as well as the voltage of the battery. We know this internal resistance of the battery, or in a wider saying, the Thevenin resistance of the rest of the circuit, equals the resistance of the load if you say the load is dissipating the maximum power. Okay, so R lowercase equals the R uppercase, or the load, and that equals 10 ohm. So this R is 10 ohm. Now this is 10 ohm, this is 10 ohm, and we know also the current here from section A. Now we should find what is this voltage. So voltage equals total current multiplied by total resistance. Total current is 2.23. This is what you got in section A. And R total is the summation of these two, because they are connected in series, 10 plus 10. And you get 44.6 volt. Section C is about the energy supplied by the source, which is actually the energy consumed by the load. Energy has this definition: energy equals power multiplied by duration of time. They gave us the duration of the consumption, 12 hours. Originally they had also given the power of this system, 50 watt. So you can multiply 50 watt by 12 hours, and that is watt hour, the energy in watt hour. But as here in section C in the question, they're asking us to obtain energy in joule, we need to multiply it by 3600, because we should not use hour, we should use seconds for the delta T. Section D says, okay, if the cost per kilowatt hour is given, what is the total cost of this system if the load is in operation for 9 hours? There are two key points here. The first one is, as the price is in kilowatt hour, so you cannot use this energy, 2.16 megajoule. This is in joule. We need to have it in kilowatt hour. The second point is, delta T, or the duration of consumption, is different from previous section. Sometimes the students may make mistakes because they use the same value they had earlier. Here they say 9 hours, not 12 hours. So these are the two key points. Now let's see how to calculate. So A, or energy, equals P times delta T again. P is 50 watt and delta T is 9 hours, which gives you 450 watt hour. But this is watt hour. I need in a kilowatt hour. But if you know how to answer question number 1, conversion of the scales of units of measurements, you can convert this to kilowatt hour. You just need to multiply this, divide this by 1000. So 450 divided by 1000 is 0.45 kilowatt hour. Then we know the cost per kilowatt hour. We can just multiply it by the total kilowatt hour. and so we have the total cost. Question number 7 is about obtaining the Thevenin equivalent model of the rest of the system. Sometimes there is no specification of which method you use. In that case, you should apply that 4-step method you had in that topic, Thevenin Norton equivalent circuits, the 4-step method. And in some cases, some exams, we give you the exact approach or method you should apply. And this is one example. Here we say you should go through successive conversions of Norton Thevenin or Thevenin Norton equivalent circuits. So you have to use this method, otherwise even if you find the VTH and RTH correctly, you won't get any marks for that. So how to convert Thevenin to Norton? Thevenin, okay, you replace the voltage source with the current source and use the same resistor in parallel. What is the value of this current source? It's this original voltage divided by the resistance, so 20 divided by 5. This is Ohm's law. Current equals voltage divided by resistance. So 20 divided by 5 equals 4. We do the same for this branch, convert it to Norton. Now, we see there are two current sources parallel. Both are injecting currents into this node. So you can add them and replace these two current sources with a single current source here. Also, there are two parallel resistors. Yes, they are parallel, even though visually they are not exactly next to each other. But as you see, the two terminals or ends of these two resistors are the same, so we say they are parallel. You can replace these two parallel resistors, 5 and 4, with their equivalent one, which is 2.22, and this is for merging the two current sources. 4 plus 4 amp is 8 amp. Okay, you see? Now, this part is a Norton-like equivalent circuit. We can convert it to Thevenin. The voltage source is multiplication of this current and this resistance, and the new resistance is the same as the old resistance, but this time it is connected in series to this voltage source. We kept the rest of the system, but now if you look at this new circuit, you see there are 2 voltage sources and 3 resistors. The 3 resistors can be merged and can be replaced by a single resistor, which is 7.72. And the voltage sources, if we look at the polarities of the 2 sources or 2 batteries, they are the same. Both of them are injecting current clockwise. So we can replace these two with a single source whose voltage equals sum of these two. 17.77 plus 12. So this is your VTH and this is your RTH. In section B, we say, okay, now you use this Thevenin model, reattach the load, and say what is the voltage drop of the load. Voltage drop of the load can be obtained by voltage divider rule. Total voltage multiplied by the same resistance divided by the sum of the 2 resistances. In section C, we say what is the power consumed by the load. Power equals VI by definition, but I don't have I and I don't want to obtain I, so I can replace I by V over R based on Ohm's law, and then I see here I got V times V over R. This can be written as V square over R. Voltage is 13.02. This is what you got in section B. This is voltage drop of the load. Be careful, this should be a square. Divided by the resistance of the load, which is 6 ohm. So this is your power, this is the power of the load. The question says when this power is maximum. The power is maximum when this load has got a resistance equal 7.72. Basically, when this load resistance and this Thevenin resistance are equal, then you can say this load is consuming power at its maximum. Now, in order to obtain that power, we need I. So I, or current, equals this voltage, VTH, divided by total resistance in this circuit, 7.72 plus 7.72. You get 1.93 amp as the total current. So P equals Ri square. R is 7.72 and I is what you got here. And you obtain this power, which is slightly more than the previous power. And finally, the last question, question number 8. Always the first part is about whether what are the total number of principal nodes and principal loops, and then say which method outperforms the other one in terms of performance. Obviously, the one with fewer number of equation variable is the best one. In that question, which you can look at the question from the paper of 2021, you can identify 3 principal loops while 2 principal nodes. So obviously nodal method will make fewer equation variables. You just need to write these numbers and these kind of sentences, and you get the full mark of section A. Section B then gives you the option to choose either mesh method or nodal method to analyze the circuit. Obviously, nodal method is better here because you will face fewer equation variables, just 2 equation variables. But it's fine if you apply mesh method if you're more confident with. But then you need an advanced engineering calculator in order to be able to get the final numbers, because you need to deal with 3 equation 3 variable problem. So we go for nodal method. And when you decided to go for a nodal method, again, there are 2 approaches. One is to write KCL for each node, and then you see from those 2 KCL you would get 2 equation 2 variable problem, and then you can decide how to solve it. Either directly use your calculator to find those variables, or to go through elimination method, or to go through matrix method. Anyway, this is one way to get the final numbers if you go for nodal method. Another way, the same for nodal method, is skipping the initial step, which is writing KCL notations, and form the matrices. How to form matrices without writing KCL? We discussed this in a class for similar examples. Also, there is a paragraph in the second page of nodal method discussion or topic you can read, and you can get how to do that. We can now review it. So you make a square matrix multiplied by a vector of variables equals the vector of constant currents. Constant currents, you need to look at those nodes. So this refers to node 1. If you look at node 1 and see what is the total constant current injected to node 1, you see in one of the branches there is a 30-volt battery and 3 ohm resistor. The current is that voltage divided by that resistance, and that's the only constant current injected into node 1. That's the same for node 2 if you look at the original circuit. Now the challenge is how to find these coefficients or the cells of this square matrix. So this is a square matrix. The diagonal elements are the conductances connected to the nodes, total conductances connected to the nodes. For example, this one, which is like cell 1, 1. You need to look at node 1 in the circuit and use all the resistances coming or connected to that node. There are 3 resistances. One is 3 ohm, the other one is 6 ohm, and the other one is 12 ohm. You need to make the inverse of them and add them, because here you need to put conductances. For node 2, again, 3 branches are connected to node 2 with 3 resistors. One is 12 ohm, the other one 5 ohm, and the other one 2 ohm. Again, you make the inverse of each one because that is the conductance, and you add them. For non-diagonal elements, you need to put the conductance between the two nodes. So here, for example, is cell 1, 2. That means you need to put the conductance of the branch between node 1 and node 2. There is 12 ohm resistor between node 1 and node 2. If you see the original circuit, you make the inverse because you need to put conductance, not resistance. And don't forget to put these negative signs. And this square matrix is actually a symmetrical matrix, which means non-diagonal elements are the same. So cell 1, 2 has the same value as cell 2, 1 because the circuit is a bidirectional circuit. You can then simplify this square matrix and you get these decimal values, and then you can try to find V1 or V2. In this example, section B, we are asked to obtain I, and I shown in the original circuit is where node 1 is. So if I know voltage of node 1, I can divide it by the resistance of that branch and find this I. So I just need to calculate V1, I don't need to calculate V2. V1 equals this fractal. The denominator is the determinant of the coefficient matrix, and the numerator is the same coefficient matrix where you replace the first column with the currents, constant currents. Why the first column? Because this is the first variable. And this is the way you obtain determinant. If this is A, B, C, D, you make A, D minus B, C. Be careful with the signs. Once you've got the voltage of that node, you divide it by the resistance based on Ohm's law, and you get the current. And this was the last question of this exam. Thank you for watching.